Okay, so hello everyone again. This is lecture number 3 on motion in a straight line. In this lecture, we will start with the concepts regarding your final few discussions regarding your average velocity and average speed. And after that, we understood instantaneous velocity and instantaneous speed. Few discussions are remaining regarding that. And then we can move on to a new subtopic, that is acceleration. We'll understand acceleration and then we can move forward with the kinematic equations. Okay, so I'm Samir Lawankar. Let's begin our discussion. Okay, so course outline for you. So right now we are on the last few concepts regarding this instantaneous velocity, and then we can move on to the acceleration point. Okay, so we started with the introduction part in which we understood basically that in this we are understanding the motion in a straight line only. Then after this we understood what is basically the difference between path length, displacement, etc. So basically, what is the difference between path length, displacement? Um, Displacement is a vector quantity, path length is a scalar quantity. So the all rules of algebraic addition, subtraction, etc. can be directly put up for path length, but it cannot be used for displacement as displacement is a vector quantity. Here, vector addition, vector multiplication has to be explained. These all explanation will be done in the chapter motion in a plane, so that will be dealt at a later stage. So right now, the second subtopic was based upon this. In the third topic, we understood average velocity and average speed. So average velocity is nothing but equal to displacement, ratio of displacement to the time taken, and average speed is ratio of the total path length to the total time taken. Then we understood the instantaneous velocity and speed. So basic concept which was regarding this was that, let us say, average velocity tells us the velocity over a time interval. What if we need to calculate the velocity at some instant? So for that concept, we understood instantaneous velocity. We started a discussion of instantaneous velocity and speed with understanding as in what happens when if you try to understand this graphically. Some numerical approach was being used, and then finally one example was being dealt in which we understood the whole situation using differential calculus. Okay, so let us start that discussion, the final discussion regarding that, and then so instantaneous speed or simply speed is the magnitude of velocity. Okay, so speed is nothing but your magnitude of velocity. For example, a velocity of plus 24 meter per second and a velocity of minus 24 meter per second both have an associated speed of 24 meter per second. So just the mod value, because it does not have any our direction is not being shown by our speed, it is always positive one. Okay, it should be noted that though average speed over a finite interval time is greater or equal to the magnitude of average velocity, instantaneous speed at an instant is equal to the magnitude of instantaneous velocity at that instant. So I will just write also this mathematically what they're just saying. So it is just saying that average speed over a finite interval of time is always greater than or equal to the magnitude of, please remember, it's magnitude of average velocity. Why? What is the case here? Why this is the case here? This is because the path length is greater than displacement, greater than or equal to this. Okay. Instantaneous speed at an instant is equal to the magnitude of instantaneous velocity at an instant. They are saying that instantaneous equal to the magnitude of instantaneous. Okay, because as the time interval has been shrink to a very very small position, so that is why there is no such new concept with average speed, because the path length and displacement would be very very close to each other, and hence average velocity and average speed are same. Just the thing happens is that because velocity is a vector quantity, therefore it has a direction. But as average speed does not have instantaneous speed does not have a direction, so everything will be positive only. Therefore, instantaneous speed will be always equal to the magnitude of instantaneous velocity at that instant, but average speed will be greater than or equal to average mod magnitude of average velocity. Why that is the case? Because the path length will always be greater than or equal to displacement. If the path length is equal to displacement, then average speed will be equal to average velocity, magnitude of average velocity. And let us say displacement can be zero also. So these all things are just the revision parts of the all the concepts which we understood in the previous two. So let us start with a new topic, acceleration. Okay, so this is a very important topic which will be understood in the several different topics also. Gravitation plays a very important role. Gravitation has a separate chapter being considered, which we will understand in the much later stage. For now, let us start with acceleration. What is basically acceleration? Okay, so let us begin. So the velocity of an object in general changes during its course of motion. Quite evident. So sometimes what would happen is, let us say there is some t is equal to 2 seconds. There is some t is equal to 4 seconds. Right? The velocity will be 5 seconds. Sorry, 5 meter per second. The velocity will be 7 meter per second. Or either it can be, let's see, 6 seconds is also being considered. The velocity is 9 meter per second. Or in some other case, it can be, let's say, velocity is 5 meter per second here, but the velocity is 50 meter per second here, and the velocity is, let's say, 120 meter per second here. So it can vary with a very different scenarios depending upon any other different objects. Okay. The velocity of an object in general changes during its course of motion. Quite evident. How to describe this change? Should it be described as the rate of change in velocity with distance or with time? There was a problem even in Galileo's time. So what he did, what was the basic reference they took? So it was first thought that this change could be described by the rate of change of velocity with distance. So they started this research topic where understanding this concept as dv by dx. Okay, let us try to understand the situation. But what was the scenario? But through his studies of motion of free falling objects, free falling as in anything which is being put up higher to the ground and without any course of action, it is just being dropped. So that there is nothing but called as your free fall. As the name suggests, free. It is not bounded by anything and it is falling, free fall. Okay. So but through his studies of motion of freely falling objects and motion of objects on an inclined plane. Motion of an inclined plane basically means that, let us say, this is a wedge and you are keeping a ball here and this is being pushed here. Okay, so motion of object on an inclined plane. Galileo concluded that the rate of change of velocity with time is constant of motion for all objects in free fall. So basically this constant is nothing but your gravitational force. As because gravitational force, this was all the research or this was all the experiments which Galileo made and concluded. Okay, so what he basically found, that that rate of change, so basically delta v by delta t was coming out to be constant. So that was his what we can say one of the conclusion. Okay, that the rate of change of velocity, so the rate of change of velocity nothing but delta v with time, so it's upon delta t is a constant for motion of all objects in free. Right. On the other hand, the change in velocity with this time was not constant. It was not constant, which was being proposed that let us do this and find some sort of concepts regarding this. It decreases with the increasing distance of fall. So it was not constant. So basically, it cannot be used as a concept to be utilized in, let's say, kinematics. So that led to the concept of acceleration as described as rate of change of velocity with time. Okay, so let's remove everything and start afresh. So what is 1 minute? Yes, so it's nothing but acceleration is nothing but equal to rate of change of velocity. So how to write rate of change of velocity is delta v upon delta t. So that is the rate of change of velocity with time. Average acceleration a bar over a time interval. Please remember a bar refers to average. Okay, so the bar refers average value. Okay, so average acceleration a bar is nothing but a bar is written as nothing but equal to v2 minus v1, that is final value of velocity minus initial value of velocity upon t2 minus t. Okay, so this is nothing but equal to delta v. So that is only been written here. So average acceleration a bar over a time interval is defined as the change of velocity divided by a time interval. divided by the time, where v2 and v1 are the instantaneous velocities or simply velocities at time t2 and t1. So these are nothing but your instantaneous. Okay, so it is the average change of velocity per unit time. Quite evident is the average change of velocity, so that is how it is changing. And the SI unit of acceleration is meter per second. How did this come? So this is nothing but your meter per second, and this is your second. So that leads you to meter second inverse divided by second, which is nothing but equal to meter second to the power minus. Simple mathematics gives you the answer of SI unit of acceleration as equal to meter per second square. That is the unit of acceleration. Let's move on. Okay, so on a plot of your velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2, t2, v1, t1. Please remember again that we try to depict it using a graph. So they are just saying that on a plot, let us say we are making a plot. Which plot they are saying? It's a velocity versus time plot. Please remember, the slope of the straight line in a position time graph tells you what? It tells you the velocity. Similarly, the slope of the straight line on a plot of velocity versus time gives you the x. So these were two different concepts. Only thing which is changed is the y-axis. Okay. So on a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2, t2 and v1, t1. So there, this would have been v2, t2 and this would have been v1. So the average acceleration for the velocity time graph in figure for different intervals 0 to 10, 0 to 10, then 10 to 18, and 18 to 20. So now we are trying to calculate something. Let us try to calculate and understand. So for first case, let us say we are trying to calculate the value of average acceleration. Please remember, it's not instantaneous acceleration. We are trying to calculate the value of average acceleration in this region here. What we just need, we need the velocity at this location. We need the velocity at this location upon a time interval. Time interval is 10 seconds. So what is the velocity at this location? It is 25. So it's 24. Okay. What is the velocity at this location? It is 0 upon time interval, that is 10. So what will be the answer? It will be 24 minus 10 upon 10, which will give you the answer as 2.4. What will be the unit? Please remember, it will be meter per second square or meter into s to the power minus 2. Okay. Moving on to the next. 10 to 18. What will happen in 10 to 18? As you can see, what we need to do, just final value of velocity, which is 24, initial value of velocity, which is 24, upon time taken, that is 18 minus 10, which will give you 8. So this is nothing but 24 minus 24 upon 18 minus 10 will give you 8. As 24 minus 24 is 0, this will give you the answer as 0. Fine. So there is no average acceleration or zero average acceleration in the range of 10 to 18 seconds. Moving on to the next range, that is your 80 to 20 seconds. So how to find it out? Final value, that is 0. Initial value, which is 24. So it is 0 minus 24 upon time taken is nothing but 820 minus 80, which will give you 2. So this is nothing but equal to minus 12. Okay. So what does this negative sign show? It shows deceleration. I'm just writing deceleration. So what is deceleration? Deceleration is nothing but opposite of acceleration. Acceleration is a positive quantity. Deceleration is a. So these all things are being understood. Let us move on. Moving on to the instantaneous acceleration. Similar to the average instantaneous velocity, we also have a concept which is called as your instantaneous acceleration. How can we define? So instantaneous acceleration similarly. Let us keep on. Okay, so how we defined value of velocity? We did delta x upon delta t. But what we know that we need to calculate the value of delta this value at delta t tending to 0. So we'll just write delta t tending to 0. This is the value of velocity. Similarly, how we will do it for acceleration? It is delta v by delta t. But this time delta t tend to 0. So we'll write limit delta t tending to 0, which will be nothing but a value. That is how we are defining instantaneous velocity. Differential form of this will be dv by dt. So this will be differential coefficient of v with respect. So the instantaneous acceleration is defined in the same way as the instantaneous velocity. Okay, that is a is equal to limit delta t tending to 0 del v upon del t, which is equal to dv by dt. Okay. Acceleration at an instant is the slope of the tangent to the vt curve at an instant. So similarly, as in the previous case, the slope of the tangent was to the xt curve was velocity. Similarly, the slope of the tangent to the vt curve, the slope of the tangent to the vt curve is nothing but your acceleration. So that was the difference, or that was how we will understand the velocity concept and the acceleration concept. Fine. So that is also been explained. Moving on. So for the VT curve shown in the figure in previous slide, we can obtain acceleration at every instant of time. So what we are just doing, we are trying to find out the value of average acceleration at each of these points, and we just drew a graph. Okay, so when we drew the graph, we got the answer as this. So for the VT curve shown in the figure previous slide, we can obtain acceleration at every instant of time. Okay, so finally what we got is this sort of acceleration. So as we also understood that the acceleration is 0 here, we got a 0 portion here, just to understand what is happening. And as it was uniform, sorry, so as it was uniform velocity here, so therefore uniform velocity leads us to constant value of acceleration. That being said, so the resulting AT curve is shown in the figure. So this is that AT curve. As you can see, AT curve is acceleration. We see that the acceleration is non-uniform over the period 0 to 10 seconds. Non-uniform, as you can see, it is 0 to 10 seconds. Okay. Then it is 0 between 10 to 18 seconds. Whatever it is 0 from 10 to 18 seconds, and is constant with a value of minus 12 between 18 seconds and 20. So non-uniform basically means that it is not a constant value. Okay. Fine. So when the acceleration is uniform, obviously it equals the average acceleration over that period. So similar to the previous discussion also, when we understood that if there is an average acceleration happening, then acceleration is equal to average acceleration. Similar to the previous case in which if there was uniform velocity happening, that velocity is nothing but equal to, in uniform motion, velocity is equal to average velocity, and similarly here also, if the when the acceleration is uniform, it equals the average acceleration over that period. Okay, so it only happens for uniform motion only. Okay, next thing, that since velocity is a quantity having both magnitude and direction, a change in the velocity may involve either or both of these factors. Acceleration therefore may result from a change in speed, a change in direction, or a change in both. Okay, so there can be change in acceleration even in the direction also. It can change with the change in magnitude also. Okay, so like velocity, acceleration can also be positive, negative, or zero. Fine. So that was all about acceleration. Let us begin the next discussion. So position time graphs for motion with positive, negative, and zero acceleration are shown in figures A, B, and C respectively. So as you can see, this is having positive A, this is having negative A. So just depicting from the graph, we cannot understand why it is having a positive value or negative value. Either what we can do is we can differentiate this graph 2 times and we can find out the answer. What is the meaning of differentiating 2 times? Why I'm saying it to be differentiating 2 times? Let us say we differentiate 1 time. What we will get? We'll get dx by dt. Now when we differentiate another time, we'll get dv by dt. So this 2 terms basically can be written as like called as double differentiation. Okay, so that is the thing here. Okay, so sometimes it is not being clear as in how is the acceleration positive or negative, but if we try to differentiate this graph, we can understand why it is being said at it is having positive, it is having negative, etc. Okay, so the position time graphs are motion with positive, negative, and zero acceleration are shown in the figure A, B, and C respectively. Note that the graph curves upward for positive acceleration. The graph curves upward. Graph curves upwards, downwards for negative, and is a straight line for zero acceleration. Okay. I can explain to you for this. Let us see. Let us take some points. Okay, let us take this to be 5 again. Let us take this to be 10. Okay, so what would be the value of mm, or okay, so let me not use any values here. Let me rightly explain. So as this is a constant value, the value of v will be the v is constant. D by dt of any constant will give you 0, and that is the reason why the c value or the c figure is said that it is having a 0 acceleration. Okay, this thing is explained. This thing is explained. Although acceleration can vary with time, our study in this chapter will be restricted to motion with constant acceleration. Okay, so let's not increase our complexity. We have already increased the complexity from moving from velocity, then average velocity, then instantaneous velocity. Now acceleration also, instantaneous acceleration also. Let's be concerned with only constant acceleration. What does it mean, constant acceleration? That if it is said that the acceleration is 4 meter per second square, then the complete analogy, complete concept will be always 4 meter per second square. Okay, maybe in future terms or in future concepts, we may require non-constant acceleration, varying acceleration, but let's not go into that. Let's understand first of all the basics, and then we can go to the advanced. Example, for the vertical movement, always the value of g is nothing but equal to 9.81 meter per second square. So this value is nothing but your acceleration value only. So acceleration is taken as equal to minus g, and hence this is a constant acceleration. So in this case, the average acceleration equals the constant value of acceleration during this interval. Okay, quite evident because we are taking it to be constant. So here the average acceleration equals the constant value of acceleration during that interval. It's the interval we are talking about. So if the velocity of an object is v naught, now let us start with first. So now we are going to obtain our first equation of kinematics. Okay. So if the velocity of an object is v naught at time t is equal to 0 and v at some time t, we have, as it's a question of constant acceleration, we can write average acceleration is equal to acceleration, which is equal to final value of velocity, which is v, initial value of velocity, which is v0. The velocity of v was obtained at some time t. The initial velocity was at 0. So what we can write, this is nothing but equal to v minus v naught by t, right? Just doing some mathematics to this equation, we'll get this is equal to v, we'll get v minus v naught is equal to a bar into t, or we can write this as equal to v is equal to v naught plus at. Okay, as we can write a bar as equal to a, just the line above explains it. So this is the first kinematics equation, that is v is equal to v naught plus at. Okay, that is if we need to calculate the value of velocity at some time t, if we know the value of initial velocity and the acceleration, it can be found. Okay, so final velocity is nothing but equal to initial velocity plus acceleration into time. This can be written as equal to v final is equal to v initial plus acceleration into time. Okay, so that is the first kinematics. Let us see how velocity time graph looks like for some simple cases. Okay, so now let us understand. So let us go a little backwards. Let us go another from some off topic and understand something different, and then we can jump to the same topic about kinematic equations. Okay. So figure shows velocity time graph for motion with constant acceleration for the following case. Okay, so an object is moving in a positive direction with positive acceleration. Okay, so this is the graph. This first graph tells you. Okay, so this first graph tells you that an object is moving in positive direction with positive acceleration. As the slope of this is positive, so it can be said that it is moving in positive direction with a positive acceleration. For example, the motion of the car in the second figure between t is equal to 0, t is equal to 10 seconds. So in this graph, B part says that an object is moving in positive direction with negative acceleration, as the slope of this is negative, but it is moving in positive direction only. Okay, only the acceleration is in negative direction. Okay, so the velocity will try to decrease. Okay, for example, the motion of the car in second figure between 80 to 20 seconds. So in this time, as you can see, the velocity will keep on decreasing, but it will always move in the positive direction only. what it will happen, let's say let t is equal to 18 seconds, the answer of velocity would have been 20. In t is equal to 18, in 20 seconds, the velocity would have been less than 8, depending upon the value. C part is an object is moving in negative direction. So if it is moving in negative direction and with a negative acceleration also. Okay, so negative acceleration simply means that the slope is negative. The slope is negative here, and it is moving as it is in the backward direction. So as velocity is a vector quantity, so the negative direction here tells that it is in the opposite sense of whatever we are moving. Because we are moving in the because we are only concerned about motion in a straight line here. Therefore, the plus sign says that we are moving in the right hand side direction or forward direction, and the negative point or negative value says that we are moving in the backward direction. Okay, so that is only been told here that an object is moving in negative direction with a negative acceleration. So because the value is increasing in negative side, we can say that yes, it is moving in negative direction only. Okay. So an object is moving in negative direction with a negative acceleration. For example, the motion of the car moving from O in the first figure, moving from O in the first figure in negative x direction with increasing speed in one of the previous examples. Okay. So it is moving in this direction with increasing speed. Okay, so that we can say as the C point. In D point, an object is moving in positive direction till time t1. It is moving positive direction till time t1, fine, and then turns back with the same negative acceleration. So because the slope is same, the acceleration would be same, negative only. The motion of the car from point, okay, and then turns back with the same negative acceleration. For example, the motion, so because it is turning back, the velocity is changed from positive to negative. What is the example for this? The example for this can be understood as, for example, the motion of the car from O to Q, let us say it goes from O to Q in the first figure till time t1 with decreasing speed and turning back. Let us say it turns back from there and moving with the same negative acceleration. So it is the speed is always decreasing and decreasing only. Okay, so there was a time at which it came out to be zero, and then it was as it was going in the negative direction. So it is keep on decreasing. Okay, with negative rate. Okay, so because it is going in negative direction, it is the velocity is increasing in negative. For example, would have occurred, let's say it was from 5 meter per second first, it went to 0 meter per second, and then it went up to, let's say, minus 5 meter per second. It is keep on decreasing in the negative direction. Okay, so till time with decreasing speed and turning back and moving with the same negative acceleration. An interesting feature of a velocity time graph for any moving object is that, very important point, please read this line very carefully. An interesting feature of a velocity time graph for any moving object is that the area under the curve represents the displacement over a given time interval. Okay, how to understand this? A general proof of this statement requires some use of calculus. We can, however, see this if it is true for the simple case of an object moving at constant velocity u. So let us say, what does it mean by constant velocity? That at any time interval, let us say we are under the being a time interval given, for any time under that given time interval, the velocity is always same. If it is always same, we say that it is having uniform velocity. Constant velocity. Okay, so we can, however, see that it is true for a simple case of an object moving with constant velocity u. Its velocity time graph is as shown in the figure. Okay, so the vt curve is a straight line parallel to the time axis, and the area under it between t is equal to 0 to t is equal to capital T is the area of the rectangle of height u and base t. Quite evident. So it is straight line, so that is the quite evident, and area under it. So this will be the area under it. Okay. So what will be the area under it? This is nothing but u multiplied by capital. Okay, is the area of the rectangle of height u and base. Therefore, area is nothing but equal to u multiplied by t, which is u capital T, which is the displacement in this time interval. How come in this case an area is equal to distance? You can understand this as this is nothing but meter per second into second. So this gets cancelled, and the answer is in meters, which is a unit of displacement. Note the dimensions of quantities on the two coordinate axes and you will arrive at the answer. Okay, so that was only the thing which I was trying to explain. That this is in meters. Note that xt, vt and at graphs shown in the several figures in this chapter. So this is position time graph, this is velocity time graph, this is acceleration time graph. Shown in several figures in this chapter have sharp kinks at some points, implying that the functions are not differentiable at these points. Let me try to explain to you whatever is written here, because you may have not learned differentiation till this point. Okay, so there's a concept in differentiation which says that if there's a sharp point happening, let us say this is a curve I make. If this is a curve, you can see a sharp point here. So if there's a sharp point here, then it is being said that at this point, the curve is not differentiable. The curve is not differentiable. Won't go into much detail of the mathematics behind it. You will understand it much more clearly when you will understand the maths regarding differentiation. I will just explain to you in mathematical terms whatever thing is required. So when we try to, let us say this is a position time graph, and if we need to calculate the value of dx by dt at that location, let's say this is location at some t is equal to t naught, then at t is equal to t naught, this value is not defined, or we will write or does not exist. Okay, so that is how we report the situation. Okay, so so basically these are nothing but called as kinks. Any pointed shape object, let us say some sort of this thing has occurred, let us say, or let us say some velocity was here, then it went from, let us say, not, let us say it was going above and above, and then there was some sort of this direction happening. So because of this kinks happening, we say that the portions are not differentiable at those locations. Okay, let's get back to the topic. So note that xt, vt, and et graphs shown in the several figures in this chapter have sharp kinks at some points, implying that the functions are not differentiable at these points. In any realistic situation, the functions will be differentiable. So these were just to explain to you the basic concepts. Let's not go into very detailing of those graphs. These were just been explained so to make you understand everything here. Okay. So in any realistic situation, the functions will be differentiable at all points, and the graphs will be smooth. Smooth as in the graph will be some that means that those will be differentiable. In any realistic situation, the functions will be differentiable at all points. So what is the meaning of this line? Functions will be differentiable at all points. This simply means that functions will be the value of dx by dt or dv by dt or da by dt will be possible to calculate at each of these locations. Okay, at all points, and the graphs will be smooth. Okay, what this means physically is that the acceleration and the velocity cannot change values abruptly at an instant. Okay, so the values cannot be changed abruptly. Won't go into much detail, just to explain, let us say what actually happens. So as we know that finding a tangent at any location or differentiating at any location gives a slope at that value. Okay, so if there is sharp kink at this location, so for a portion which is on the left hand side, the slope would have been some sort of this value, but on the just right hand side the value would have been this, which is not possible for a location. The slope would be always only one for a particular instant or for a particular location, and that is why. And because what does it say? Let us say I make a velocity time graph, right? If I take a velocity time graph and this is the velocity time graph, the velocity cannot, for a same time, for some time t is equal to t naught, there cannot be two different velocities, right? So that is the only explanation being made in this line. So if I draw a graph slope like this and if I draw a slope like this, then this is not possible, because in real life situations at some time t is equal to 0, it will always have a velocity which is constant. Therefore the graph will be smooth only at every location, so that whenever we try to calculate the value of tangents, we will get a single. So that was the explanation regarding this portion. So what this means physically is that the acceleration and velocity cannot change values abruptly at an instant. Changes are always continuous. So they keep on happening, but it is not the case that a single value of time will have two different. Okay. Moving on. So the basic conclusion of this slide was that the area under the velocity time curve can give you the value of displacement. Okay. In that time interval only. So when every basic concept is covered, every basic concept is completely covered, we have understood all the different things. We started with the position displacement part, then we started then the next concept we covered was regarding your Then the next one we covered was regarding your average speed, average velocity. Then the next concept we considered the concepts of your acceleration. So that all being said, let's now jump to the main discussion topic about this chapter, that is kinematic equations for uniformly accelerated motion. Okay, so kinematic equations for uniformly accelerated motion. Please remember for this complete chapter, always the acceleration is uniform. Acceleration is uniform. Okay, fine. That being said, let's start the discussion. Okay, so for the uniformly accelerated motion, we can derive some simple equations that relate displacement, time taken, initial velocity v naught, final velocity v, and acceleration a. Okay, so a relation between final and initial velocities v and v naught of an object moving with uniform acceleration a is already obtained and is provided below. So this was the first kinematic equation which we derived in the previous case also. How we derived it? Just a recap. We used average acceleration a bar as equal to v minus v naught upon t minus t naught. As we used the for initial case as equal to 0, this was nothing but v minus v bar v naught upon t, which changed to a bar was a, so therefore it changed to v minus v naught is nothing but equal to at, and therefore we got and therefore we got that v is nothing but equal to v naught. Okay, therefore v is nothing but equal to v naught. That was the first kinematics equation. This relation is graphically represented in the figure. So that is how we can understand this figure. From this figure also, there is a constant acceleration happening. In this scenario, it is positive value. The time is being taken place. This was the initial velocity, and after some time t, we got the final velocity. So what is the final velocity? This final velocity is nothing but equal to v naught plus a times. What is the area under the curve? The area under the curve will be nothing but area between instants 0 and t, which will be equal to area of this triangle ABC plus area of the rectangle OECD. Okay. So how to calculate this? So as this is V naught, this will be V minus V naught. Okay, so calculating the value of triangle first, that is nothing but equal to half into V minus V naught into time taken. So this base will be time. Okay, calculating the value of rectangle, this will be nothing but E naught multiplied by T. Right, as explained in the previous section, so this is only been written here, it's half into v minus v naught into t plus v naught into, as explained in the previous section, the area under the vt curve represents the displacement, we know, right? Therefore what we can write that x, that is displacement, is nothing but equal to half of v minus v naught into t plus v naught into t. Okay, from this equation we know that we can write v as nothing, v minus v naught as nothing but at. So this can be written as at. Therefore what we got, x is nothing but equal to v naught t plus, I just put this value here first, and therefore plus half a t square, and this is nothing but your second kinematics equation. Okay, please remember, these kinematic equations will only and only be used when we are having uniformly accelerated motion. Okay, so but v minus v naught is equal to at, therefore x is nothing but equal to half at square plus v naught, or x is equal to v naught t plus half at square. Okay, so till now we have two kinematic equation. Let us first write those kinematic equation. The first equation says that v final is nothing but equal to v initial plus acceleration into time, and similarly the displacement happening is nothing but equal to v naught t plus half at square. X is equal to v naught t plus half at square. So please remember this. Now let us move forward. Let us understand the third kinematic equation and we are good to go. Okay, so above equation can also be written as x is equal to v plus v naught by 2 into t. Okay, so how we can write this? We can understand from this point also. So just look at this location. Okay, so how we can say this is nothing but x is equal to this is nothing but v t by 2 minus V naught T by 2 plus V naught T. It can be written as Vt by 2 plus V naught T minus V naught T by 2 will give you V naught T by 2. So just writing this, we can write V minus V naught into T by 2. Right? So we can written as x is equal to V minus V naught into T by 2. I think I made a mistake. Yes, plus minus. Sorry. I'm really sorry for this. This will be plus. Okay. So because plus V naught T minus V naught T by 2. So this will be plus V naught T by 2. Okay. That is V plus V naught into T by 2. Okay. So we know that average of any two quantities can be written as V bar. So V bar is nothing but equal to V naught plus V naught by 2. So this is just the mean value. This is just the mean value. Okay, so how do we calculate the mean? It is nothing but summation of all the quantities divided by number of quantities. Okay, so therefore x is nothing but equal to V plus V naught by 2 into T. This is equal to V bar into T, where V bar is nothing but V plus V naught by 2 for constant acceleration only. Okay, please remember everything. The first thumb rule which we need to remember is that everything which you are understanding is for constant acceleration only, or it is for uniformly accelerated motion. Okay, so above equations mean that the object has undergone displacement x with the average velocity equal to the arithmetic average of the initial and final velocities. So if we remember the initial and final velocities, we can find out the displacement as nothing but equal to average velocity multiplied by time taken. Okay, so now let us do one thing. So we have x is nothing but equal to V bar into T. From the first kinematics equation, we know that V minus V naught is nothing but equal to AT. So therefore T is nothing but equal to V minus V naught by T. V minus V naught, V minus V naught by A. Okay, just try to put this in this. Okay, so what we will get? We will get x is nothing but equal to V plus V naught by 2 multiplied by V minus V naught by A. Okay, so the numerator can be changed as A plus B into A minus B, which will give you V square minus V naught square by 2 into A. It changes to V square minus V naught square equal to 2AX, or we can write this as equal to V square is equal to V naught square plus 2AX. And this leads us to the third equation, third kinematics equation, which is V square is equal to V naught square plus 2AX, or we can write this as V final squared is nothing but equal to V initial squared plus 2AX. Okay, so that is how we calculated or derived all the three different kinematics equations. Just write, and I'm just writing this for quick reference and revision also. So the first kinematic equation states that the final value of velocity is nothing but initial value plus acceleration into time. The second is that the total displacement occurring is nothing but equal to V naught T plus half AT squared. The third thing is that we got at this V square, that is V final squared is nothing but equal to V initial squared plus 2AX. Okay, so if we have the time given in the question, we can use the first equation. If we have the displacement given in the question, we can use the second equation. So that depends on the question which is being asked. Okay, fine. This being said, let's move forward. Thus we have obtained three important equations, that is V is equal to V naught plus AT, then x is equal to V naught T plus half AT square, and V square is equal to V naught square plus 2AX. Okay, connecting five quantities. So what are these five quantities? V naught, V, A, T, and X. So these are the five quantities which we can interrelate. Okay, so if any of these four are given, we can find out the fifth, some sort of numerical adapted to calculate. So questions can arise from this. So please practice questions regarding this concept, and we can move forward. Fine. So this being said, these are the kinematic equations of rectilinear motion for constant acceleration. Please understand each and every line here. Kinematic equations. Okay. Kinematics is a branch which helps us to understand the motion, to describe the motion. Of what? Of rectilinear motion. What does rectilinear motion mean? Rectilinear motion means motion in a straight line. Okay. So only and only there will be movement in one direction, either move forward or either backward, or let's say in upward direction, either upward, other down. Okay, so it depends whether you take x-axis or y-axis, etc. Okay, for constant acceleration. Constant acceleration means that the value of a is. It is important to understand each and every word written so that everything will be clear when all these concepts come into picture. Okay, because there are several concepts to be understood in this complete physics of 11th and 12th. Okay, fine, let's move on. So the set of equations above were obtained by assuming that at t is equal to 0, the position of the particle x is 0. Okay, so that was one of the assumption we took. We can obtain a more general equation if we take the position coordinate at t is equal to 0 as non-zero, say x naught. So x naught is some value. Okay, so it is not that we are starting only from the reference position. We may start from some another position also. Okay, so we are saying that let that position be equal to x naught. Then above equations are modified, replacing x by x naught to so how it changes. So the first equation does not have any value of that, so it is nothing but same, that is v is equal to v naught plus 80. Another equation has, so we will change it to x minus x naught is nothing but equal to v naught t plus half at square. Therefore this will be equal to x naught plus v naught t plus half at square. Okay, similarly second will be nothing but v square is equal to v naught square plus 2a into x minus x. Okay, so this is your first, this is your second, and this is your third. Okay, that is being written. So v is equal to v naught plus 80, x is equal to x naught plus v naught t plus half at square, and v square plus v naught square plus 2a into x minus. Moving on. So now let us understand one of the questions using methods of calculus, and let's end this lecture then. Okay. So by definition, what is just we are trying to find out all these equations using method of calculus. Okay. So please, I'll try to go very slowly so that you can understand each of the concepts written here. Okay. So because you will be very new to this differential calculus concept, so let's try to understand each and everything from the start. Okay. So first of all, this is the quite clear. Instantaneous velocity we have defined at equal to dv by dt. Okay, so these things can be used like this. So we are just interchanging. So we can write dv is nothing but equal to a multiplied by dt. Okay, now we are integrating both sides. So integrating, so this is an integral sign. So we can put integral sign on both sides directly. And always when we put the integral signs, we have to put some limit. Okay, so that limit is basically from where to where we are trying to integrate. Integrate is basically a infinitesimally small area being calculated under. So as we do the summation, this is an integral form for the infinitesimal form of summation. Okay, so integration is nothing but infinitesimal form of summation being done. So here the initial value is starting from v naught, final value is v, initial value is 0, final value is t. Okay, so what we can say, it is nothing but integration of v naught to v dv, which is equal to a is a constant, so we can take it outside the integral sign, 0 to t dt. Okay, so first tool we can say that anything which is, so it's nothing but dx is nothing but 1 times dx, right? So integral of 1 times dx is nothing but x. Let's say I write it as x1 to x2. So this is nothing but going from x1 to x2. So we can write this as equal to x2 minus x. So that is how the integration is being done for this. Okay, so therefore what we can say, we can write this as nothing but equal to v minus v0, and similarly this can be written as a is equal to t minus 0. So this is nothing but equal to v is equal to v0. So that is how we design the. Moving on further, now for the differential calculus of the second portion, we know we used v is equal to nothing but dx by dt. This also is being understood when we understood the instantaneous velocity concept. Similarly, we can write this as equal to dx is nothing but equal to v dt, right? Now, just in the similar form, dx is nothing but equal to v dt. Okay, putting the integration on the both sides. Here x is going from some x naught value to some x value. Here the value, every time the limit of the integral will be depending upon the differential form. Okay, so here differential form is t, but time t will be going from 0 to t, right? When x is going from x0 to x naught. The left hand side will be x minus x naught, as it was explained earlier only. Okay, now we know that this v is also a function of some time t only, right? We understood in the first kinematics equation, this v is nothing but equal to v naught plus at. So let me just write this here. So it's nothing but v naught plus at dt integral 0 to t. So now this time you cannot put this at portion outside because this is a function of t. Okay, so now let me just rub and calculate first of all this integral sign. So it is integration of 0 to t v naught plus at dt. Okay, so this can be written as, we can separate these. So it is nothing but integral 0 to t v naught dt plus integral 0 to t at dt. Okay, as v naught is constant, v naught can be put outside. So it's integral v naught 0 to t dt plus a is also constant. Let's put out integral 0 to t dt. Now another rule I will explain to you. So integral, let's say 0 to t only, or let's say I make it more general. Integral, let's say t1 to t2 t to the power n dt is nothing but equal to t to the power n plus 1, okay, upon n plus 1. Limits t1 to t2. So what I will write this is equal to, this will be t2 to the power n plus 1 minus t1 to the power n plus 1. This will be n plus 1. This will be n. Therefore, for this case scenario, integration of 0 to t dt will be equal to t square, because 1 plus 1 will be 2, upon 2 from 0 to t. Putting those values, you will get t square by 2 minus 0 square by 2, which will be equal to t square by 2. Okay, so that is how this second integration is being done. And when you will try to understand this, this will be nothing but equal to v naught t plus a into t square by 2. And the left hand side was x minus x naught only. So therefore we got x is equal to x naught plus v naught t plus half a t square. That is how you got second kinematic equation. Okay, let me stop it here only. In the next lecture, I will again try to revise this because one time it got erased. So I will go very slowly again, and then we can move on to third kinematic equation, and then we can move forward. Okay, so let me stop it here. We'll understand these all concepts in the next chapter, in the next lecture. So the course progress for you. So right now we are on the fifth concept, that is kinematics equation for uniform accelerated motion. We have completed the introduction part, position, path length and displacement, average velocity and average speed, and instantaneous velocity and speed and acceleration. Okay. After kinematic equation, we'll move on to relative velocity, and that will be the end of this chapter. Okay. So thank you so much. We'll meet in the next lecture.